Mr. President, Mr. Chairwoman. Now, first of all, I would like to, today, I don't feel comfortable sitting, but if you can hear me. Okay, I apologize for this. I would like to express my sincere gratitude to the IGF committee, which made this honoring invitation to me. It was a pleasure and an honor to accept. And the reason is that not only our friendship, but the fact that IGF is an example to all national sister societies like the Greek Society of Experimental Mechanics of Materials. Now, when I accepted the invitation, I had a dilemma concerning the issue that should be presented. I had a dilemma between something that is in progress, very modern, or a review of some concepts that could be considered as closed. So I decided to present some thoughts about the stress intensity factor. And finally, I think that the choice was correct. Attending this conference yesterday, the day before yesterday, I found out that more than half of the presentations are related with this concept, which is so familiar to all of us, but there are some details that should be reconsidered. So we'll discuss a few topics about the stress intensity factor. And as you will see at the end, this topic is something like the Hydra of ancient Greek mythology. You cut a head, I mean, you solve a problem, and then you find out that there are two more heads generated, two more problems or more that should be solved. So, fracture mechanics is an adventure that started more than a century ago by the pioneering works of Kirsch, English, Griffith, and so on. However, more than a century later, I think that there are some issues that are not completely closed. And the most important is the stress intensity factor. We use this concept and we have a general overview, but there are some questions. And if you follow a discussion, a current discussion in ResearchGate with a very provoking title, are the days of the stress intensity factor numbered? Is it something that will die soon? You can read in this discussion very controversial points of view. Some of the participants consider that K is without meaning. Some participants consider that it is the very heart and the pillar of fracture mechanics. About the final answer, we can see it later. Now, according to my opinion, the most critical issues that should be reconsidered are three. Some unnatural effects that are obtained when we solve problems using linear elastic fracture mechanics in 2 dimensions, which lead to the unnatural overlapping of the cracked lips. Then there is a distance between the finite domain we have in practical applications and the infinite domain considered when we solve problems analytically using linear elastic fracture mechanics. And finally, there is a problem between what is a mathematical crack with a singular tip and whether it is close or not to what we machine in practice. In this issue, late Professor Lazarin has very important contributions, which are numbered here, some of them, with his team, and which also shaped our point of view concerning the stress intensity or concentration around cracks, which are not cracks, in fact. Now, let us start with the first issue. I'll try to be as short as possible because I think that the most important thing now is discussion after the presentation. Now, what is overlapping? What you can see here, if we solve a problem theoretically in 2 dimensions in linear elasticity, the displacement field leads to what is called overlapping of the crack lips. The upper lip, the red one, overpasses the lower lip and obtains its position. Obviously, this is not a possible case to be seen in practice. However, it is predicted clearly by theoretical solutions. And it is long ago that trying to solve this problem, starting from Barenblatt in the theoretical field, and much later by Banks-Shields and her team, who tried to avoid the problem of overlapping or contact crack lips, introducing a very sophisticated, arcan grips for URK mode loading. So Harry's team, my mentor's team, also made work in this field, and they gave a condition according to which overlapping could be avoided. Unfortunately, if we look deeper in the solution, it seems that under specific combinations of load, geometry, and material, overlapping cannot be avoided. And for their solution, after 50 degrees of crack inclination, overlapping is again a result of the theoretical analysis. Much later, in the frame of a PhD study, Dr. Markides introduced a very simple idea, very simple as a concept, but extremely complicated concerning the mathematical formulation and solution. What is the idea? To superpose to the initial ill-posed problem of overlapping lips an auxiliary inverse mix problem, which transfers the elliptical terms of the displacement field, the terms that are responsible for the overlapping, and generate the respective contact stresses that are to be exerted in order for the lips not to be able to move one on the other. You can see here the overlapping lips. You see the red one, which is the upper lip, becomes the lower lip, and the methodology adopted to overcome this solution. In fact, the linear terms of the displacement field rotate the crack as a rigid body in a position called false crack by Theoharis, and then the elliptical terms of the displacement field transfer the point along the lips to their new position, which finally leads to overlapping conditions. And that is to avoid overlapping, but in this case, we have to take into account the inevitably generated contact stresses. What was the contribution of this PhD is that it was possible to calculate the contact stresses in case of an infinite domain. You can see here the expressions for the contact stresses along the lips. And what is to be emphasized is that this inversion is partial. We invert portions of the elliptic terms of the displacement field, and what these portions are depend on the specific geometrical conditions of the problem. So the factors P and delta, the portions of the elliptic displacements that are to be inversed, should be checked and discussed in each case independently. Now, just for comparison, we could consider the intact disk with a linear segment equal to the crack and crack disk. And now we can calculate the contact stresses, which in the problem of the infinite medium are constant all over the crack. You can see that the contact stresses are relatively close to the stresses that are developed in the linear segment of the uncracked. And the same is true for the rotation. We have a rotation of about 2 degrees in the cracked plate. We have a rotation of about 1.3 degrees in the intact plane. Now, this was an exercise because the solution was relatively simple, since we had an infinite domain. However, this is not the case in practical applications, and the most widely used practical application is the determination of the stress intensity factor, the fracture toughness, using the Brazilian disk. It is used quite widely all over the world in case of very brittle materials like marble, stones, concrete, because we cannot implement a direct tension test with very brittle materials. There are two standards, and there are expressions which provide kappa, but we will see that perhaps they are far away from the actual result. There are problems, for example, the basic solution by Hongro considers point loads, in fact, or loading along a predefined length, the contact length between the jaws and the disc. what is the extent of the contact, in fact, and what is finally the factor. When we started dealing with the cracked finite disk, two problems together, finite domain and cracked disk, we were very conservative. We considered initially a very short crack because we wanted to avoid interaction of the crack with the boundaries of the problem. And also, we considered a distribution, not point load, a distribution of stresses along a varying contact length. This is perhaps the innovation. We accepted, and this is the case, that while the load increases, the contact arc increases also. It is not, as was suggested by Stavros, that we load the disk at an angle of 1.5 or 2 degrees. This is a varying quantity. So with these assumptions, it was possible to solve the problem assuming that overlapping is avoided, which means that for specific configuration, you can see what happens in practice. The initial crack is rotated by the linear tensor displacement, and then the elliptic terms translate the tip to a new position. So the final tip is not the initial one as a material point. This rotation was validated experimentally. Using the DIC technique, we managed to calculate the final shape of the crack, which is not anymore linear. It is an elliptic. You can see the deformity. And also an angle of rotation, which is very close to the theoretical predictions of the infinite domain. Now you can see here the predictions for the stress intensity factor. Remember that we adopted the mathematical crack concept. So there is a stress intensity factor. Obviously, it is reasonable and it has natural meaning as long as the geometry does not lead to negative stress intensity factor, mode 1. So this solution was very close to the result by Atkinson, 1982. It's very familiar to all of us. He predicted that assuming point loads, the limit is 30 degrees. Using a contact arc of 2 degrees, we found something like 29.3, which is very close. Up to this limit, the solution is acceptable from the natural point of view. Obviously, the next step was to consider contact. Under specific conditions, crack inclination, contact cannot be avoided. Overlapping can, but contact no. Avoiding overlapping, we generate contact stresses. So the target, the challenge was to calculate the contact stresses in this finite domain. I will skip, obviously, all mathematical details. It was a very difficult problem from the mathematical point of view. However, these are the results. So we have naturally accepted stress intensity factors, both K1 and K2, for the whole range of the possible crack inclinations beta. You can see here the details. And what is more interesting, we validated by the method of caustics our main assumption. What is the main assumption? What is the crack? What is the contact arc? We do not know the extent of the contact arc between the jaws and the specimen as the load increases. So we had to accept the solution of the intact disk. And we have to validate. You can see here the validation. The upper results are for the intact disk, the caustics for the intact disk, and the lower figure is for the disk with a crack. You can see that the length of the caustic is almost identical. So our assumption for short cracks is validated using the solution of the intact disk for the crack, for the contact length is sufficient. Now, something that we couldn't expect. When we calculate mode 1 stress intensity factor, we suppose that the crack is under opening mode. We have to apply tensile loads. What we do in practice? We apply compressive loads parallel to the crack, and we assume that these two configurations are identical. They are not. In case we adopt the ISRM suggestion, the fact that the curved jaws impose restraints does not permit simulation and identity of these two configurations. The difference is huge. So what we are saying by using the ISRM standard is not perhaps the actual stress intensity factor under movement. And what is left now is to consider long cracks. Adopting the ISRM standard we do not have short cracks, especially the CCNBD, the chevron cracked notched disc. The length of the crack is not very short. Obviously, this problem cannot be solved, assuming a crack, a mathematical crack, and we consider a solution with an elliptical discontinuity, and then using the semi-axis, the minor semi-axis to zero, we can go close to crack. Again, the mathematical solution was not very easy. However, the final result is quite encouraging. You can see here the predictions for the stress intensity factors and those by Atkinson. Exclude the term in parentheses, which are the normalized factors, and which is much more complicated in our case. We accepted the actual loading condition, which is a parabolic and not a point load, as accepted by Atkinson. We obtain results which, to our surprise, are very close to each other, even for low cracks. You can see here an example with a crack equal to 40%. And the agreement between our solution and that of Atkinson is close enough. Only the short crack solution is far from the predictions for extreme geometry. What is left now is something that is usually ignored. If we have a disk with a crack, which is loaded not parallel, neither normal to the crack, the equilibrium conditions cannot be satisfied unless we accept a distribution of frequency forces, of friction forces. It is not possible for the disk to be in equilibrium with a crack loaded not normally, neither parallel. This problem, in fact, what is the necessary distribution of friction forces on the disk below contact arc, couldn't be solved until Dr. Hemsley contacted us because he found in our paper, in our first paper, something that was not correct according to his opinion. Dr. Hemsley is Dr. Cooper, in fact. Perhaps you know a pioneering paper around 1970 with the fracture of glass cylinders. It is a pioneering paper in the study of Brazilian disc. So the family name was Hemsley, and with his help, we could solve the problem of the friction. It is not Coulomb friction, it's not symmetric, because the friction should be zero at the axis of symmetry. It is a combination of two types of friction. The first type of friction is the traditional Coulomb friction, and the second type is a friction due to deformation. So if we want to keep overall equilibrium, we should consider the effect of friction forces as we consider it in the case of contact lips, because avoiding overlapping by inversing the elliptical terms should be used when we have also friction, that is the factor T, as I mentioned. Now, the last issue is some implications caused by the actual shape of the crack, which is not in fact a crack. We use the standards of ISRM, but as Ying Xu et al. Said, if we ignore the actual geometry of the notch and the dimensions of the crack, the result that we obtain could be erroneous. So we undertook an attempt to find the stress field in case a finite disk is loaded and the discontinuity is in the shape of a rectangular notch with rounded corners. Obviously, we ignored the actual distribution, and we found some interesting results concerning the distribution of the displacement field, which could lead to lips in contact, depending on the width, on the initial width of the notch. What was more important, however, is that all stress components remain bounded. There is not a singular field, which means that perhaps the stress intensity factor is not the proper one when we deal with problems in practice where the crack is by no means a mathematical singular crack. So we tried to plot the stress components in terms of the stress concentration and not the stress intensity factor. And what was very important also is that it strongly depends on the width of the notch that we machine. And also, there are differences on the stress concentration at various points of the crack notch, of the crown of the notch. So as a next step, we tried to impose the actual load distribution, which is a parabolic distribution of pressure. The results were validated again. The field is bounded. You can see here the limit for the two cases, tension and compression parallel to the crack, which are not identical. There is a huge difference here. And skipping some details, we came again to the finite element solution. Perhaps someone wonders, since we have in the 21st century finite elements, do we need analytical solutions with so many assumptions and perhaps difficulties in validating them? The answer is yes. Any finite element model somehow must be validated. And unfortunately, experimental results are difficult to be obtained, for example, on the lips of the crack. So we need analytical solutions, at least for validating the numerical tools, which are very useful for parametric analysis, for example. Yes, of course, if we want to carry out a detailed parametrical analysis, we need finite elements. So we made an analysis of the various factors that influence the stress concentration factor. And the most disappointing one is that our solution cannot take into account the third dimension. Since we use complex potential techniques, which are two dimensions by default, we ignore the actual stress distribution along the thickness of the disk, which is not ignorable by no means. And then we made a thorough analytical parametrical analysis, but the details are more or less expected. And the last step was to check our numerical and analytical solution in practice with a specimen made of rock, because ISRM and ASTM standards are mainly used for brittle materials. So using the 3D DIC technique, we managed to validate the fact that we do not know a priori the point where cracks start. It can start from any one of the points of the notch, depending on the geometry, either from the center of the crown of the notch or from the tips of the crown of the notch, or it can start also from the interface between the crack, between the disc and the jaw. The most important conclusion was that when we apply the compressive force according to the standard, the distance between the lips increases very smoothly and almost linearly up to 70% of the maximum load. Then up to 95% of the load imposed, we have a change of the slope. If we insist at this point, we concluded definitely by the experimental results that after 95% of the force that we consider that the specimen fractured, we have already crack propagation. The two halves of the disc are kept together exclusively due to the action of the curved jaws. So it is quite possible that the load we use to calculate stress intensity factors or fracture toughness overestimates, or in fact underestimates reality. It's very dangerous. That is why during a conference organized by Professor Bertolin, we proposed that the ISRM standard should be drastically reconsidered, because the load we assume as fracture load is not the actual one. Fracture has started already well before the final crack appears. So I think that this is the adventure of my team on the field of stress intensity factors. I am sure that more questions are now than before my presentation, but the conclusion that I would insist is that there are too many things to be done, even in concepts that are considered closed, and in fact they are not. Thank you very much.